It's a little bit of a sad story if gravitational potential energy is the only potential energy at our disposal. And since an object in free fall, at least, has a constant acceleration, there's really a lot that we could already do with gravity. But here we're going to consider a spring system, and we don't really have any tools up to this point to deal with that. But it'll turn out that the spring potential energy is a very useful idea, and it lets us handle this system as long as we ask the right questions about it. Let's suppose, so that we don't have to worry about gravity right at the moment, that we have a horizontal system. And no harm in thinking of this surface as being frictionless. And let's suppose that we have a spring. It's not stretched, it's not compressed. At the moment, it's at its natural length. And attach a mass to it. So the mass is located, not going anywhere, just let it sit there. It's located at a special point called the equilibrium point, or equilibrium position. And this position is so useful in considering springs that very often the equilibrium position is just taken to be the zero for the coordinate system. Now, if we take the mass and we pull it back, let's suppose that we pull it a little bit to the right and stretch the spring out. Well, we're having to apply some extra force to stretch the spring, which means the spring itself is applying a force to the mass, trying to pull it back. And that's going to be the spring force. If the mass is pulled back to a position X, then the stretching of the spring, really delta X would be a great thing to call it, but because it's X minus 0, that's just the same as X itself. But it can be useful to think of X not so much as the position of the mass, but how much it's stretched beyond the 0, or if we draw the mass to the left of the 0, that's how much the spring is compressed. If the spring obeys Hooke's law. Now, for a spring, this is always going to be an approximation, but it can be a very good approximation. Then it will turn out for the picture above that the spring force, looking at the X component, is going to equal some constant K, that's the spring constant, times the amount the spring has stretched. But to make things work out properly, because the X in the picture is a positive number, but the force component should be a negative number, we need to put a negative in the equation. That's if we want the K to be a positive number, and we do. I guess that's the tradition. K is called the spring constant. And large K implies stiff spring. So the spring constant is a measure of the stiffness of a spring. The larger the K, the stiffer the spring. If you wanted a unit for the K, don't know if it's so worth writing down, but the SI unit for the spring constant. That almost looks like English. The SI unit for K, or the spring constant, is just a Newton per meter. Nothing too special there. We could actually see that if the spring force in the horizontal is the net force of the object, Well, we know that from Newton's second law, the net force is equal to the mass times the acceleration. But if the spring force is the only force present, then this would be the spring force x component is the mass times the acceleration x component. But the spring force is negative kx, would equal the mass times the acceleration. And the acceleration would be the negative of k divided by m times the x. And the main thing I want to point out here is that the acceleration is not constant. And chapter 2 was all about constant acceleration. Since here the acceleration isn't constant, we can't use chapter 2 skills to handle the spring system. Well, it does turn out, here's the good news, the spring force is conservative. And remember that a conservative force always has a corresponding potential energy. It's kind of a black box if we're willing to take the book's word for it. The potential energy, let me try that again. The potential energy of a spring is 1/2 times k, the spring constant, times the amount of stretching squared. So the spring potential energy, also often called the elastic potential energy, is 1/2 kx squared. In a problem, if we were looking at the motion of a mass attached to a spring in the horizontal, so just like the pictures up above, but we'll draw some new pictures here. If we have an initial and a final, and suppose that we pulled the mass back and released it at some point, and it's moving to the left with speed v initial, put a spring in there, and the current position of the mass is x initial. So it may be, I guess, that we had to pull the mass farther out back here somewhere than we released it, so when it's at x initial, it has some speed. And now it's moved to the other side. Maybe the new position is x final. It's compressing the spring. So, highly compressed spring. And it's gone over, so maybe it came over farther, and it started back the other way. The exact direction of the motion does not matter. The math doesn't really care which way it's moving, but sometimes we have to look at it and figure out whether it's going in the positive or the negative direction. Then, in this case, conservation of mechanical energy is going to show up. Here's probably the overriding theme of this chapter. The energies, the object's moving, so it has kinetic energy. It's attached to a spring, so there is spring potential energy, but it doesn't have a vertical motion. So here we don't have to include the gravitational potential energy. So the mechanical energy is made from the kinetic and the spring potential energies. On the left-hand side, we'll have the initial values, add them together to get the total mechanical energy. And on the right-hand side, we'll have the final values added together to get the total mechanical energy. And the kinetic energy, 1/2 times the mass of the object times its speed squared, its initial speed squared, plus the potential energy is 1/2 k times the x initial squared, and this will equal the same thing but with the final values. And this equation then, in this situation, can be very useful, and you'll see an example of this in this section's examples out there, I suppose. May also point out that if we had a more complicated situation, oh boy, suppose that we had an incline. So even here, it does show up in the notes. And we had a mass. Let it be frictionless, the surface, once again. But that mass is attached to a spring, so we might pull it down and release it, and it oscillates back and forth, back and forth. Well, do we have the tools to handle that motion? It gets a little bit complicated, but in essence, it's now, well, we're attached to a spring. We have the spring potential energy. It does have a vertical aspect to its motion, so we would have the gravitational potential energy, and the object is moving, we'd have the kinetic energy. So here, it'd be kinetic energy initial plus the gravitational potential energy initial plus the spring potential energy initial would then equal the same, but with the final values. So even for the motion of one object, things can get a little bit complicated. Nevertheless, this whole idea of the conservation of energy, and in particular the conservation of mechanical energy, can be extraordinarily useful, both within the classroom and without.